Hey everyone, welcome back. In this video, we're going to talk about our inverse tangent function, and this is going to be the last of our inverse trig functions that we kind of formally discuss. We talked about it briefly in an earlier example video, but we really only need our sine inverse, cosine inverse, and tangent inverse functions, because if we want to work with our other inverse functions like secant inverse, cosecant inverse, or cotangent inverse, we can always do some algebraic trickery, use those reciprocal identities, and work with these original three more popular trig functions and their inverses instead. So we're going to go through that exact same process for our tangent function that we did for our sine and cosine functions. And so the first thing we looked at is the graph of our entire tangent function. Well, not the entire graph of it, that's impossible, but more than one period of it. And so here we have 1, 2, 3, about 4 periods of our tangent function graph. And what we can see from the graph of our tangent function is that it does not pass that horizontal line test. No surprise there. None of our trig functions do. So in order to make it an invertible function, in the sense that its inverse is also its own function, we're going to have to restrict the domain of tangent to make it a one-to-one function. So for our cosine function, we restricted the interval to 0 to pi to make it a one-to-one function. Technically, that would work here for tangent. It would be a one-to-one function, but it would be kind of discontinuous because of that weird middle vertical asymptote that we would include on that interval. For sine and sine inverse, we restricted to the interval from negative pi over 2 to positive pi over 2, and that's the choice that is made for tangent and tangent inverse as well. Because on this restricted interval from negative pi over 2 to positive pi over 2, our function is continuous on that interval, no weird jump discontinuity due to a vertical asymptote. And furthermore, we go through the entire range of our tangent function on that restricted interval. So save ourselves a little bit of board space. I'm going to go ahead and this time erase the part of our function that we don't need. So we don't need everything on our tangent function outside of this interval from negative pi over 2 to positive pi over 2. So let me go ahead and get rid of all of that. All right, so we've figured out that we need to restrict our tangent function to the smaller interval from negative pi over 2 to positive pi over 2 in order to make it one-to-one and therefore invertible. Now let's go ahead and reflect the graph of tangent of x across the line y equals x to see what the graph of inverse tangent or arctangent looks like. And so remember, we can think of these vertical asymptotes as being described by equations like x equals negative pi over 2 and x equals positive pi over 2. Remember, for a function and its inverse, the roles of x and y essentially switch. So instead of having equations like x equals negative pi over 2 or x equals positive pi over 2, on the inverse, those are going to turn into equations like y equals negative pi over 2 and y equals positive pi over 2. And so now when y is equal to a constant, that gives us a horizontal line instead of a vertical line. So our vertical asymptotes turned into horizontal asymptotes as we reflected them across the line y equals x. Furthermore, on the graph of our tangent function, we know we go through the point 0, 0. So that means our inverse tangent function is also going to go through the point 0, 0. That doesn't help us out too much, but the rest of the behavior of our tangent function is helpful in finding the behavior of our inverse or arctangent function. So we're abusing our point notation just a little bit here, but this is really just describing how our tangent function is behaving as we approach this vertical asymptote at x equals negative pi over 2 from the right-hand side. So as x gets closer to negative pi over 2 from this right-hand side, we see that y is decreasing without bound or going down towards negative infinity. And so now we also know that the roles and behaviors of x and y just essentially switch for a function and its inverse. So on the graph of our inverse, it's like we'd be looking at the ordered pair negative infinity, negative pi over 2. And the way that would be interpreted is over here, the x coordinate going towards negative infinity means we are heading off towards the left, and the y coordinate approaching negative pi over 2 means as we head off to the left, our graph has to approach this now horizontal asymptote instead. Similarly, if we look at the kind of right end behavior on this restricted domain, that is, of our tangent function, as we approach x equals pi over 2 from the left-hand side, our tangent function is increasing without bound, going towards positive infinity. So if we switch the roles of x and y, on our inverse tangent function, x would be going towards positive infinity as y approaches pi over 2. So if we graph a lot of those points and keep that behavior in mind, The graph of our inverse or arctangent function is going to essentially look like this. Probably the coolest looking of all the inverse trig functions in my opinion. But again, we're not really going to be using the graph of inverse tangent for much of anything like graphing it or graphing transformations of it. It's all just helping us kind of relate to the unit circle and the need for this restricted domain. So when we are thinking about evaluating an inverse tangent expression using the unit circle, just like for sine inverse, we're thinking about being on that special version of the right half of our unit circle. So before we look at some of those examples together, let's go ahead and write down some of those important facts about our new function here. So we can denote it as using our normal inverse function notation. So we can call it tangent inverse of x, or we can denote it using that arc notation. So it'll also be called arctangent of x. They're exactly the same thing. So let's see, what about the domain of our inverse tangent function? That's going to be the set of all x values such that x can be anything, right? It's just the range of our tangent function. That range is all real numbers. The domain is also going to be all real numbers, or the interval of x values from negative infinity to positive infinity. If we want to be lazy, we could just write that as capital Blackboard R. Remember, that symbol denotes all real numbers. All right, and the range of our inverse tangent function are just the outputs or the y values that we see on our graph here. And let's see, those y values go from negative pi over 2 to positive pi over 2. And notice these are exclusive inequalities, not inclusive. We can never actually obtain these values of negative pi over 2 or positive pi over 2 as an output from our inverse tangent function. And that makes sense because that would imply that we can actually input negative pi over 2 or positive pi over 2 into the original tangent function, but we can't. That corresponds to like one of those spots where we get division by 0 or a vertical asymptote. Ooh, one last thing we need to check out. Does our inverse tangent function have any symmetry? And it looks like it does. It looks like it also exhibits that odd symmetry or that rotational symmetry around the origin. Hello everyone, in this example we have a couple expressions we want to evaluate together. Most of them are involving our inverse tangent function. So we'll start off with evaluating tangent inverse of the square root of 3. Then we'll discuss tangent inverse of negative 1000. Then we'll finish off with tangent of cosine inverse of negative 1/3. All right, so let's take a look at this first expression together. Here we have arctangent or tangent inverse of the square root of 3. And we have to remember is that what comes out of an inverse trig function is going to be some angle. Let's go ahead and call that angle theta. And remember, for that restricted domain and range for our tangent function and its inverse, we know that our angle theta is going to be such that it is between negative pi over 2 and positive pi over 2, or on the right half of that special version of our unit circle. And so furthermore, what we know is that if we take tangent of this angle theta on the right half of our unit circle, we're going to get the output of tangent to be equal to the square root of 3. So now we have to think back to our unit circle and figure out where does tangent take on this value. And so all the points on our unit circle are labeled with the x and y coordinates, but tangent, remember, is the ratio of the y coordinate to the x coordinate. So that is not always labeled. So it might be nice to actually take some of those points on your unit circle, like this one over here, square root of 3 over 2, comma 1/2. And then off to the side of it, I like to write the tangent value. That's the y divided by the x. So that's like 1 over square root of 3 or square root of 3 over 3 for this first point, not the one we're quite looking for here. But if we go up to that other point on the right half involving the square root of 3, that's the one we eventually want to work with. Right? Our y coordinate divided by our x coordinate gives us our tangent value. That's equal to exactly the square root of 3. So what is our angle associated with that point on the unit circle? The point being 1/2 square root of 3 over 2. That gives us our tangent value of 3, and that is the angle of pi over 3. So the last thing we have to check is just make sure, is pi over 3 in that correct interval from negative pi over 2 to positive pi over 2? And it looks like it is. So that means we have found our answer to tangent inverse of the square root of 3. It's equal to pi over 3. The next expression on our list that we want to try to evaluate together is tangent inverse of negative 1,000. And so we might try to reference our unit circle here, but we should see is that any of those ratios of the y to x coordinates that we take from known points on our unit circle are never going to be equal to exactly negative 1,000. So in this case, we would essentially just use a calculator to help us evaluate this expression. All right, so in practice, a calculator is definitely what we should use to evaluate this expression, tangent inverse of negative 1,000, but we can kind of be clever and do it in a tricky way as well. If we think about the graph of our arctangent or inverse tangent function, well, what happens if we plug in x equals negative 1,000 into our arctangent function? Well, we're heading off way over here to the left on the graph, and as we head off to the left, we approach our horizontal asymptote. And we get really close to our horizontal asymptote really quickly here. So what we know is that tangent inverse of negative 1,000 is going to be approximately equal to the value of our horizontal asymptote here. And we have to just remember now, well, tangent inverse had a lower horizontal asymptote at negative pi over 2. So if you plug tangent inverse of negative 1,000 into your calculator, you're going to get some decimal approximation as its output. If you then put negative pi over 2 into your calculator, evaluate that, you should see those numbers are very, very similar and close to each other, because tangent inverse of negative 1,000, as we can see from the graph here, is pretty close to or approximately negative pi over 2. All right, so we have one last expression to simplify and find the value of in this example here, and that is this composition of tangent along with cosine inverse of negative 1/3. And so negative 1/3 is not going to be one of those exact values on the unit circle, so we won't be able to just evaluate cosine inverse of negative 1/3 and plug that angle into tangent. We could approximate that with a calculator, of course, but we can actually do this exactly and find the exact answer to this special composition. But we're going to have to be very careful in how we approach it. To get started, we're going to try to evaluate our composition from the inside out. So the first thing we have to think about is the innermost piece, cosine inverse of negative 1/3. And so we've kind of approached some of these problems before. What we know about cosine inverse of negative 1/3 is that it's going to give us some angle theta such that theta is between 0 and pi, or on the top half of our unit circle, and cosine of theta equals negative 1/3. And so with that kind of substitution, we can maybe make this look a little bit nicer and friendlier by replacing cosine inverse of negative 1/3 with that placeholder angle theta. We're never actually going to find this angle theta. It's not one of our known angles, but what we're going to see is that we don't actually need to know it exactly. All right, and so now there's a couple different ways in how we can make progress in the problem from this point on. We can use some trig identities or some right triangle trigonometry, and I'm a big fan of the right triangle trigonometry approach. All right, so what we know is that cosine of theta is equal to negative 1/3. So there's going to exist some right triangle out there with these proportions, such that if we take the ratio of the adjacent side to the hypotenuse, we get that ratio to be negative 1:3. We know that the only way our angle is going to plug into cosine to give us an output or an x value of negative 1/3 from the unit circle is if that angle is in the second quadrant. So that can help us kind of orient our right triangle here and maybe use a reference angle and things like that. But really, we just have to keep the correct quadrant in mind at some point along the way. So what I'm trying to get at is we don't necessarily need to use a negative value on this right triangle. If we do use negative values within our right triangles, we have to make sure they are assigned to the correct side lengths. The hypotenuse will always be positive. The adjacent and height or opposite side lengths may be negative. We want to choose those side lengths to be negative or positive such that it places our triangle in the correct quadrant. So if we wanted to be in the second quadrant, we need a negative x value and a positive y value. So this triangle is set up relatively correctly. I guess we could have flipped it to make it look like it's in the second quadrant, but not all of that is necessary. All right, so why is this right triangle going to help us evaluate our tricky composition up here? Because after we've rewritten our composition, we're essentially just taking tangent of this angle, which we can do using our right triangle trigonometry, right? What is tangent of an angle theta in right triangle trig terms? Tangent is opposite over adjacent. So we don't know our opposite side length yet, but we're going to be able to find that using our Pythagorean theorem. And if we divide that by our adjacent side length of -1, well, then we will be able to evaluate this original composition. So we know that -1 squared plus this unknown, let's call it y squared, is going to be equal to 3 squared. So 1 plus y squared is equal to 9, y squared is equal to 8, and y is going to be equal to plus or minus the square root of 8. But here we need y to be positive to ensure that we end up in the second quadrant for this angle. So y is going to be equal to the positive square root of 8, which we could simplify, if we wanted to, as 2 times the square root of 2. And so what this now allows us to do is evaluate our original composition. What is tangent of cosine inverse of -1/3? Well, all this right triangle work was dealing with that cosine inverse of -1/3 part. That helped us set up this right triangle. And now we can take tangent of this angle within our right triangle to finish evaluating this expression. So tangent is opposite over adjacent. That's going to be 2 times the square root of 2 divided by -1, or just -2 times the square root of 2. So we have to be very careful when we encounter these compositions of a trig function with an inverse trig function inside. We're essentially going to have to treat that inverse trig function as outputting some special angle that'll help us set up a right triangle. And then once we have that, we can rewrite the problem as a simpler, more familiar right triangle trig problem. And then we can use our right triangle trigonometry to evaluate that outer function and the overall composition. So in this example, when we did that here, we found that tangent of cosine inverse of -1/3 is equal to exactly -2 times the square root of 2.